Perfect. So
Yeah, thank you very much for organizing this amazing workshop and also for letting me speak about probing singularities in GR with quantum fields. This is a joint work with Abhay Ashtika, Tommaso De Lorenzo, and Adrian, who gave a talk 1.5 days ago, actually. And yeah, to understand why this is an interesting question, or why we think it's an interesting question, let's first review the statutes of singularities. By the way, the papers are also in the talk, so I can only give you a very brief upshot, and then you can refer to the papers for the juicy details. Okay, the statutes of singularities is mainly described in general relativity by the singularity theorems of Hawking and Penrose, and also Jarrow has some, and it involves the definition of geodesic completeness. That is, basically, a geodesic can be uniquely extended. Every geodesic can be uniquely extended to infinite range of affine parameter. That is to say, when we have a geodesic observer that is a freely falling observer, that this observer traveling on the geodesic will not see any pathology whatsoever. The pathology could be, and that is what refers to singularity, if you have an intersection of geodesics or that geodesics end abruptly. And this is exactly what a space-time singularity does. At space-time singularities, geodesics end abruptly and the tidal forces become infinite. So this is a very daunting statement, and we can say, well, now we can go home. Why do I have to listen to this talk? Because what should I do here? Well, the history of physics has actually taught us some lesson in giving up too quickly on singularities. And I'll give you an example you all know. This is the Coulomb potential, which describes the hydrogen atom. As you can see, it has a 1/r divergence at r equals 0. And classically, electrodynamics, which is a very powerful theory, predicts that for the hydrogen atom configuration, the electron will hit the r equals 0, where the energy density become infinite within nanoseconds. But our everyday observation tells us that this is a total bupkis, so it cannot be true. And this is something interesting. Although these completeness notions seem very mathematical, they're actually physical because they can be verified or falsified by experiment and observation. And we see that the hydrogen atom is stable, and quantum mechanics gives us the explanation. Quantum mechanics tells us that the Hamilton operator is self-adjoint, essentially self-adjoint, to be more precise, and this generates a unitary time evolution. But what does it mean physically? Physically, it means we have a wave function that now describes the bound state electron. This is a complex element of a complex Hilbert space, and it's subject to probabilistic interpretation. And this is an important part because the wave function itself has support at r equals 0, the 1s orbital. However, the probability of finding it is 0. So we see that in quantum theories, the probabilistic measure plays an important role for the consistency of these theories. So we cannot view the state without looking at the probabilistic measure. And this tells us something about the fundamental structure of nature. So singularities can serve as a portal to understand nature better. And this is just our idea. Our idea is to revisit the statutes of physically interesting dynamical singularities, which occur in important spacetimes like the Schwarzschild spacetime and the Friedmann-Lemaitre-Robertson-Walker spacetime. And here I will restrict to FLRW. However, the treatment is not tied to the specific symmetry, so it's a general principle. We'll make some comments later on. And our question is, will the test field and observers constructed from them, for example, the stress energy tensor, remain regular in the QFT sense across the Big Bang? And for those who have no time and don't want to listen to me, I'll give you the answer right away. And surprisingly, it's yes. But as you can see, there's a catch. And that is exactly how I formulate the question. I formulate the question like in the QFT sense. And to understand the answer, we have to understand the question first. And that means we discuss now the nature of quantum fields. So to not get blurred by any curvature effect or whatsoever, let us just go to Minkowski spacetime. Because if the nature of quantum fields should be in the purest way, we should see it in Minkowski spacetime. So the quantum fields in Minkowski spacetime are given by this particular form. You see that. The Minkowski spacetime will be referred, any Minkowski quantity I use will have this small circle here. Okay, you see my cursor. Yeah, this is just the combination of creation and annihilation operator and plane wave solutions. It fulfills the Gordon equation. But as we have heard already several times in this workshop, this phi of x is not the quantum field. It's an operator of distribution. So it's not operating on the space of functions. And this now will become very important, because what is the quantum field as in the operator sense is the one that is smeared against the test function. So you can think of it as the following sense. So you have this distribution phi 0 of x, and you take a function f that tells you what is the support of this function, and then you get the extended object of the quantum field. So that is a very rough idea how you can imagine. And this object now is self-adjoint operator on the Fock space satisfying the wave equation in the distributional sense. And we take as the test function the Schwarz functions on the Schwarz space here. So the important part is now, what means regular in the QFT sense means that this integral is well-defined, leading to a self-adjoint operator, and this object here, and this equation of motion is fulfilled. That's the thing which tells you the QFT is in some sense consistent. Okay. And the distribution character you can see already when you look at the 2-point function, which is a bidistribution. So this object here is, of course, not well defined for each value of the coordinate and the prime coordinate. And we routinely use it. And we also routinely use 1 over r, which is a singular function, but regular distribution, satisfying the Poisson equation of the spherical Laplace operator. And I mean, it's obvious that this equation here is not very well defined when we set r to 0. So then we get something equals 4 pi infinity, and then this box of 1 over 0. So this is not very clear. But in the distribution sense, this is totally well defined, and we use this object very regularly. So now the question we actually want to pursue is, do quantum fields and observables constructed from them remain well defined across the Big Bang? So our example just as operator value distributions. Okay, so let's go to the example, and let's go to cosmological spacetimes. Here, for brevity, I use the conformally flat FLRW spacetime, but for example, Adrian is also working on the when the Gaussian curvature is non-zero. So the scale factor is given by polynomial in eta. Eta is the conformal time, and of course, the singularity is at eta equals 0, because then the line element becomes degenerate. Now, to understand what happens at this, if this is well defined across the Big Bang, we have, of course, to extend the spacetime, because we want the support of our object to extend over the singularity to see if there is a real problem. And therefore, we do the obvious way. We just glue a copy of the spacetime at the singularity. There's a more sophisticated way. We also have it in the paper, but this sophisticated way reduces to the obvious way in FLRW. So here we are, in some sense, precise, but quick. In that sense, we somehow have a putative Minkowski spacetime. Okay, we take minimally coupled massless spheres just for brevity, but there is, of course, you can extend it. We also comment on the paper on this. You have a mode decomposition with now the basis function E, and they fulfill a certain equation of motion, and they have a normalization. And this normalization comes from the symplectic product. But the symplectic product, just to give you a foreshadowing of what we will see, is actually well defined on the full manifold, or the full extended manifold, and in the classical theory even. So therefore, we could say, maybe when we take distributions which are much more, let's say, well behaved in the sense of that if a function diverges, it diverges, no problem. But if a distribution diverges, we have to see whether this is really bad for our theory. Okay, so now we have to look what this E does, and then we see what actually is going on for FLRW. And we look at specific examples, radiation at the dust of the universe. For the vacuum, we choose the bunch state as a vacuum state. That is just that at this phi, we get the positive frequency Minkowski mode. You can choose another one that is not, it doesn't depend on this particular. The solution to the wave equation we have just seen is given by the Hanker functions. And these Hanker functions for general alpha is just as it is, but for integer values, for some integer values, they have a very nice form. For example, we can get the Minkowski one, and for radiation dominated, we get the conformally covariant Minkowski. So we have one Minkowski over the scale factor, as you can see. And for dust, we get another term, and this is because the box phi equals 0 is conformally covariant whenever the whenever the Ricci scalar is 0. And for the radiation, it is 0, but for the dust, it's not longer 0. Therefore, we get this additional term. And this is important later. Okay, so let's look at the radiation dominant because also physically most important. Some models say that before inflation, there was the radiation dominated phase. So this is the phase in some models, at least, that is considered to be the state of the universe bordering at the Big Bang. Okay, but I'm not a cosmologist, so please don't kill me for this statement. So we have a radiation-filled universe. It's linear in eta. We have a Ricci scalar, and the volume element now is given by eta to the power 4. So we get this volume element, which is, of course, when we have to smear, we get a volume element here. So phi of f is constructed as the integration of the field against the test function, and we get conformally Minkowski, as I just said. So we have 1 over eta. This diverges, of course, but we get a volume element, and this integral is then on the full extended manifold, totally well defined, and the field operator itself does not sense a problem here. For the 2-point distribution, it's the same. So the divergence is also 1 over eta integrated against this. So we get eta to the power 3. So this object here is also well defined once it gets integrated against test functions. Okay, but this is not, that's very boring because this is just somehow linear. So if the field is well defined, then all product of it are well defined, except when we now look at composite operators. That means we evaluate the product at the same position. So that is that digs deeper into the ultraviolet behavior because these operators have a higher adiabatic order, you can say. And so we look at the phi square, the renormalized operator product, evaluated at 1f. So now we can only smear against one test function, but since this is a conformally, covariant theory, it is of course, we get the Minkowski result when we subtract the David-Schwingert counter term, and we get 0 here on the whole space-time manifold. And you can see that because the phi square is always proportional to the Ricci scalar, and the Ricci scalar here is 0, so we don't expect anything, so that's okay. However, for the stress energy tensor, this picture changes because we now apply a derivative, or the double derivative, and we get 1 over eta to the power 6. That is, as a function, it is disaster. But let's see what happens for distribution. So we can smear it with an a to the power 4, and we are left with 1 over eta square divergence. However, as a function, I said, disaster. As a distribution, not so much, because this is actually subject to well-defined distributions that are the homogeneous distributions. And how you can see that, this 1 over eta, whenever alpha is an integer value, it fulfills the following integrals. So you can derive these distributions by taking derivatives of a locally integrable function that is a logarithm. And the logarithm here is a well-defined inner distributional sense on this full manifold. So therefore, we can just throw the derivative on the Schwarz functions. The asymptotics are safe because they are Schwarz functions, and we get a well-defined integral. So also for the stress energy tensor, although it senses the singularity, the consistency is not violated in the sense of that this is still a well-defined operator value distributions. And that you can say, well, you can look at conformally Minkowski. Maybe this is just because of that, and there's no surprise. Okay, so let's look at the dust-dominated universe. And for dust-dominated universe, we get extra terms here.
Mark, you got 1 more minute.
1 more minute. Okay, we get extra terms, and this is, of course, this is well-defined. We have, because also we get a stronger suppression by e to the power of 8 with e to the square. For the square factor, because we get e to the power of 8. For this renormalized product, it's proportional to Ricci scalar. This is 1 over eta, but this is facing e to the power of 8, so it's well defined. There's no problem whatsoever. For the stress energy tensor, it's actually less badly behaved than the radiation dominated, so this cancels, and we just are left with a logarithmic divergence. However, it introduces an ambiguity because the one particle Hilbert space is not is not well defined as long as we take an infrared cutoff. But this is an infrared issue, which happens at every time. So there's no problem here. So this has nothing to do with the singularity. So let me just wrap it up very quickly. So we've seen that the Big Bang singularity is remarkably tamer when we consider the QFT objects as operator-valid distributions. The classic fields diverges, but you can show that the one particle Hilbert space norm is finite, but you have to, of course, take care of this particular infrared issue. We have similar results for the Schwarzschild black hole. The Schwarzschild black hole, the leading singularity is logarithmic, but it faces a volume element that is quadratic in R. So also here we see that the field operator has no problem. And if you're interested specifically in the Schwarzschild, and if you like also path integral methods, there's earlier work I did with Stefan Hofmann from the LMU that where we look at the functional Schrödinger representation. That is a functional generalization of quantum mechanics in principle. And we looked at what is the analog of unitarity and self-adjointness in the QFT picture in curved spacetime by studying the properties of the Hamilton operator in these particular theories. Okay, thank you. Sorry.
Thank you very much for your talk, Marc. So now we have some time for questions. So please raise your hands. Okay, I don't see any raised hand for the moment. So may I ask one question myself?
There are two questions. No, that was an applause. Yeah, okay.
Yeah, they're clapping. So could you distinguish between a bouncing cosmology and this kind of standard Big Bang singular geometries with this renormalized stress energy tensor? Is it very sensitive to it?
Yeah, in principle, it is of course sensitive in the sense of that when you have a bouncing cosmology, you don't have a singularity, right? So this object, in principle, you don't need to use distribution theory. So of course, then you can be much less accurate in this sense. So what is our idea is, but this is just like very vague idea, is that the distributional property is inherent to quantum theory. So that means whenever we go into ultraviolet, it might be that this distributional character is always present. But if you have a bouncing cosmology, you can in principle describe it as a smooth manifold. So here, I think you don't need to be so rigorous. So you can see it already, it should be much more well-behaved. But what you can see, for example, that you don't get derivatives in that sense on the Schwarz functions, right? So the integral is well-behaved even right from the beginning. The other thing is you have to, of course, fulfill the equation of motion here. So it might be that that this is even less tricky here. Yeah.
Okay, I see. Thanks for the answer. So we got a question from Morgan Lynch. Please, could you?
Okay, yeah, hi. Thanks for this presentation. My question is motivated by that original slide you had for the hydrogen atom. And in regards to what happens in a Schwarzschild black hole. So what actually happens to quantum fields at the singularity? Is there some sort of shell structure, or does it just smoothly go to zero, or what's actually happening at the center?
Yeah, that's a very interesting case. So with this method, you see the same as here. You get this suppression and everything. These operators are well behaved. But when you look into this functional picture, you can, in some sense, make a time resolution, right? Because you have a Hamilton operator, you have a Schrödinger equation, a functional Schrödinger equation, and you can see what's actually happening. So you see there is a strange structure. So this is particularly described here in the last one, where you see, depending on the L, you see certain like wiggles of the probability density, and in principle, it happens the same as for the hydrogen atom, that the singularity is the population is depleted at the singularity.
Yeah.
So you see that at some point it goes down and then it fades to the singularity and it becomes zero.
Okay, cool. Thank you.
Thank you, Marc, for this wonderful talk.